Good morning. I was waiting a little bit for Atano, but that's okay. Today, we're going to talk about electrical safety testing for ventilators. And you'll remember that we're talking about doing electrical safety testing to comply with the IEC 62353 standard, which is a little different than and somewhat fewer tests than following the IEC 60601-1, which would be a requirement if you are a medical device manufacturer in your design validation testing, as well as in your final assembly testing in the factory. That would need IEC 60601-1. For everybody else, the IEC 62353 has been adopted internationally so that we can do a better job and quicker job of getting the electrical safety testing done, and so that we do not shorten the useful life of the medical device, because there are tests in the IEC 60601-1 that may shorten the useful life of the medical device. So IEC 62353 is what we're going to follow. Before we begin that, I want a little review question here. And Maria, you can open the poll in just a minute. The question is, which of the following IEC 62353 testing methods should be used for ventilator testing? So I want you to get in your mind a picture of a ventilator. I don't care which one, the one you're most familiar with, and think about the questions that we need to ask ourselves in the decision tree in the standard about which test method. We know that most ventilators, as a matter of fact, everyone that I know that is electrically powered has a switch, an on-off switch. That means that we would not use one of these test methods. The next thing is, we know that that the device that most of the devices that we're going to be talking about today in ventilators are an IEC 60601 class 1 device for electrical safety testing. So that means we typically will have an accessible test ground point, protective earth point, and whether or not we have a conductive non-grounded test point for our touch current leakage. So here's the question: which of the following test methods should we use for ventilator testing? And you get to just pick one. So Maria, you can open the poll and so they can respond.
All right, it looks like a majority have answered. I'm going to leave it up just for a few more seconds, so make sure you answer the poll question.
Okay, and we're ready for the great reveal. And the correct answer should be direct method. Why? Because the direct method is the one that provides test results that are as similar as possible to the test results that we would get if we were following the IEC 60601-1. So if we are a manufacturer's field service organization, that's going to make our quality manager very happy, because the results that we will get with the direct method IEC 62353 will be, we say, correlatable. They will be able to be compared very well, very closely to the test results that were obtained in design validation and in the final assembly testing. So there's a continuity there. We get a continuity of the test results, which is really important. So let's move forward. Ventilators are really important devices. They are life support devices. You don't get a ventilator if you don't need a ventilator. There are lots of different reasons that we would use a ventilator. There are a lot of different modes of ventilation, modes of operation of the ventilator. There are ventilators that are called non-invasive ventilators. That just means that they are designed to be used with a mask or something and no endotracheal tube for the patient. Endotracheal tubes are for patients who need ventilation, who cannot control their airway, and or who would have otherwise a blocked airway. So we will provide an endotracheal tube, and we will ventilate that patient. If they have, or they may have an injury in the main part of their body, a pneumothorax or something like that, or acute respiratory distress, which is one of the things that happens in COVID-19. The COVID virus produces acute respiratory distress at some point for some patients. And if we don't ventilate, then we lose the patient dies. So it's really, really important that these ventilators are safe and effective for clinical use, which is why we're doing the testing on them and why we do electrical safety testing. All right. So they contain a breathing circuit, a control system, monitors for ventilation, alarms, and so forth, all of which need to function properly. Remember, yesterday we talked about answering the question not only of what test method and standard should we use, but we also asked ourselves the question, how often should we test? So again, this worksheet here is what the University of Vermont Biomed Department here in the United States uses to determine a risk-based inspection frequency. So they're looking at 5 criteria. They're applying, there's a weight for each of the responses for each criteria. And we pick just one response for each criteria and then get a total risk score. As I said yesterday, if that total risk score is 13 or higher, then we would test twice per year. In the case of ventilators, this is the exact assessment that the University of Vermont goes through with a ventilator as a category of medical device. Their total risk score that they came up with is 17. Obviously more than 13, therefore, ventilators should be tested twice per year. Most of us would test electrical safety each time because it's a life support device. But you're going to test electrical safety at least once in those 2 times per year. Frankly, for myself, my opinion is I'm going to run electrical safety every time that I do the testing, because medical devices, especially ventilators right now, are in heavy use. They're used all the time, 24/7, 24 hours a day, 7 days a week. You could say 365 days a year, and they are, but this past year, in a much bigger number of ventilators operating that much. So things happen when you operate equipment like that. And so it's important that you do all of the testing. So we'll test ventilators twice per year, including the electrical safety. So to do the testing, we will want for sure the electrical safety analyzer. And again, we're going to talk about and show you the ESA 615 electrical safety analyzer. We do have other electrical safety analyzers that could also be used. And when you do the rest of the testing beyond just the electrical safety test, you will need some sort of ventilator test or gas flow analyzer. And in our case, we would direct you to the VT650 or VT900A. All right, so we will always, as I said yesterday, we will always evaluate or look at the physical condition of the device. Is it clean and decontaminated to begin with? And in this pandemic, this is really important, very important, that it's clean and decontaminated and disinfected before you even put your hands on it. As a matter of fact, these days, you probably ought to be thinking about wearing gloves as well as a mask and probably either eye protection or a face shield whenever you're doing anything if you're working inside a hospital or medical facility. We'll look for physical damage to the external parts of the ventilator, any physical damage at all, hoses, everything. The display intensity should be adequate so you can see it during the daytime. The switches and controls should be operable and correctly aligned. There should be inventory control numbers and labeling, and all of those should be able to be legible. That means you should be able to read those labels, and all the inlets and hoses should be in good condition, power cord, accessory cables, and there could be a charger because some ventilators have a backup battery. Or might be designed for portable use, like in an ambulance or portable use in an aircraft. And in those cases, a lot of times they're going to be operated on battery. If there are any filters or vents, we want to make sure that those are clean. So all of this physical inspection is always part of what we're going to do, even if all we're doing is electrical safety. And now we come to our electrical safety testing. Remember yesterday we talked about the need to do measure the resistance of the ground wire. So we're going to do that. We're going to measure the leakage current to ground, and we're going to do the touch current, or previously known as chassis current. Touch current is going to be measured. So we're going to go through that, and we're going to document all of our measurements. We're going to look at them against the testing limits from the standard. And I showed you those yesterday, and those are available in the book chapter that is available for download when you take this ventilator testing course in the Advantage Training MDQA series. So these are the tests that we're going to do. Now I have another question for you. True or false? Ventilators typically do not have continuously electrically conductive patient connections. True or false? And Maria, you can open the poll question again, please. This should be quick and easy for everybody to answer. So,
Okay, I'm closing the poll now.
okay. All right. And here is the big reveal. It is true that ventilators typically do not have continuously electrically conductive patient connections, which means we will probably not have any patient connections that need to be tested in terms of applied part testing for our electrical safety procedure. Now, high-end ventilators that you would typically find in an intensive care unit or long-term ventilator unit might have some other patient parameters that are integrated into the ventilator. But typically, the patient parameters that we would worry about are going to be part of patient monitors, which will be used alongside the ventilator. So you'll have the patient monitor connected to you and the ventilator connected to you if you're a patient that needs them. But the ventilator typically does not have the patient monitor built in. It's monitoring other parameters like respiratory rate, it might display inspiratory or expiratory flow rate. It will always display the tidal volume, the inspiratory and expiratory tidal volume will be displayed. And for each mode of ventilation, those are the things that will be displayed. Sometimes you'll have end tidal carbon dioxide measurements that are being made. If you're in anesthesia, the anesthesia system will include a multiple respiratory gas monitor that will give you inspiratory and expiratory inhalational anesthetic gases and agents concentrations. But again, those are typically, they might be integrated into the anesthesia system, but typically the ventilator itself would not have those things. So again, there won't be any applied part tests typically. So when we set this up, and you're going to see the India team, Ravi and the India team set this up this way, we will set the electrical safety controls at startup mode. We'll insert the cables and connections to the electrical safety analyzer. So we're going to connect the ventilator to the electrical safety analyzer. We're going to plug the safety analyzer into the mains power and turn it on. And then we're going to do something that I didn't talk about yesterday, but is really important. Before we do any electrical safety testing, we're going to look at the line voltage, that is the voltage coming into our test instrument from the mains power, from the wall panel or a wall connection or ceiling connection, wherever we're getting our mains power. And why are we doing that? Because we have found outside the United States and outside of Western Europe, the electrical distribution system in buildings, including hospitals, do not always provide a proper ground or reference point. The neutral might be connected, you might have two hot wires, L1 and L2, both carrying voltage. That's actually not the way it should be wired for a hospital, but you may find that that is the case. You may find that that means that you don't have a ground, or that your neutral wire is not really a return wire at all. And that's going to present problems for the safety analyzer as well as the medical device. So we're going to always at the beginning check the voltage on L1, L2, and ground to make sure we have a proper ground, a proper reference point. So Ravi, maybe you can demonstrate that so they can at least see that we're able to see each of the conductive wires for mains power and the voltage test. Once we're done with the voltage test, then we go on to things that we talked about yesterday, like the ground wire resistance or protective earth resistance or protective earth bonding. All of those words mean the same thing. We need to measure the resistance of the ground connection to make sure that it is the resistance is as low as possible, and should be zero, but sometimes you just can't get it to be zero. It should be as low a resistance as possible, because you will remember from your training, your school training, electrical current follows the path of least resistance to get back to its source, the path of least resistance. So we're going to make sure that we look at the resistance and make sure that it is as close to zero as possible. And I apologize if I didn't explain that exactly yesterday, but it is always the case, no matter what category of medical device we're testing for electrical safety. We will first always make sure that that ground wire resistance is appropriately low resistance. So the way we're going to do that is we're going to connect, attach our red test lead to the null pin on the electrical safety analyzer. This makes it convenient for you to run the test. And the reason that we're doing this is because we are measuring electrical resistance with a 2-wire system, and therefore we have to zero out any resistance that is in our test lead before we make the measurement. So we're going to ignore the test lead resistance and show only the resistance of the medical device when we get ready to do the test. So we're going to zero the test lead first, connect it to that null pin, and press the F5 button, which I believe, which is the 0 button on the electrical safety analyzer. Once we get that zeroed, then we will move the red test lead to the accessible ground point on the wherever it exists on the medical device. Typically it's on the back, but not always. So you'll find where that accessible ground point is, and you'll make your ground wire resistance measurement to that point. So you connect the red test lead to the accessible ground, and then look and see what the resistance displayed on the electrical safety analyzer is. Now, once we've done that, the next thing that we need to do is measure our leakage current. And the first leakage current that we need to measure is the ground wire leakage, all right? So the way that we do that is, again, here we say select direct differential alternative, and that would be true, but we should already, unless this is a brand new medical device that we've never had before and we're doing acceptance testing, we should already know that we're going to use the direct method or whatever the method is that we're going to use from IEC 62353, and we should have made sure that our electrical safety analyzer is set to use the IEC 62353. Okay, so we pick the direct method. We're going to connect that, leave that red test lead connected to the accessible ground test point, and we will measure. This time we're going to push the microampere button on the front panel of ESA, and then we're going to observe the value that we see. Now, what we want is a worst case condition. And so what we're going to do, therefore, is we will measure AC plus DC on the electrical safety analyzer. We could look at each one individually, but we want to see the worst case leakage, which would be the combined leakage of both DC and AC values. So we're going to be looking at that value in microampere on the display screen of the electrical safety analyzer. All right. We will make this measurement both in power on and power off, normal and reverse polarity in each case, and in each case we will measure with the ground open and the ground closed. So we're going to run through this test several times in order to make sure that we have found the worst case electrical leakage value. Okay. Now be careful switching between normal and reverse polarities. And there's actually a delay built in, and you actually go through an off position on the electrical safety analyzer to prevent sharp current impulses from damaging either the medical device or our safety analyzer. All right, so we've measured leakage to ground. Now we come to equipment leakage, which is our touch current leakage, which was previously known as chassis leakage. For this measurement, we need to move that red test lead to a conductive test point where in an area of the medical device that the patient could touch or that the caregiver, the clinical staff person may touch while they are touching the patient. You remember what we said yesterday about sometimes there is no such conductive test point. The whole covering of the medical device it's covered in plastic, which is an insulator, and there is no place, non-grounded place for us to get onto. And in that case, we will use that 4 centimeter or 10 centimeter square of aluminum foil. We will attach it to the touchable surfaces of the medical device and tape it down with some sort of tape and clip our red test lead to that aluminum foil in order to make this touch current measurement. All right, and hopefully Ravi can demonstrate that. I looked to see if I had photographs of that. I don't, because we usually, when we demonstrate it kind of live on camera. So this touch current test will also be done with power on, power off, because we're using the direct method now from the IEC 62353. So we will test with power on and power off, normal polarity and reverse polarity. And we will also do the single fault test for opening ground and closing ground and make sure that we find what is the worst case leakage current, and that's what we will document. Okay. All right. That's all that I have for the presentation. And I think then we're actually ready for questions, Maria, before we go to Ravi's demo. So are we ready with questions?
Yes, it looks like we've got a few flowing in. I will pass these over to Atanu to send to you to answer.
Yeah, hi Jerry.
Hi.
Yeah, so we have one basic question. Actually, it's though not related to this webinar. It's basically the question was like, what is the difference between ISO 17025 and IEC 62353? So it is not part of our current. We have already covered it in our January webinar.
1025 has nothing to do with electrical safety. It's a completely different standard about something else. So they are not related.
Yeah. Okay. So next question is, any possibility the air and moisture inside the patient circuit can be conductive?
No. Think about it. How would that ever happen? How? It's not. It never will be. So the answer is no. And in any case, it's just like in infusion tubing. Is the saline, which is a crystalline and could conduct electricity if there was enough salt crystals in the fluid, it's still not part of the electrical safety testing. So the answer is no. The tubing itself, none of that is electrically conductive. It is not, there's no reason why. You can measure it if you want to, there won't be anything there.
Yeah. Okay. So next one is that regarding the aluminum foil that you have discussed. So there is a few query on that. Like any particular size of aluminum foil, and can you give the dimension of aluminum foil used for measuring the touch current?
Oh, they weren't listening. I said a 10 centimeter square of aluminum foil, all right?
Yeah, 10 by 10. Yeah.
10 by 10 by 10 by 10, 10 by 10, okay? And you
Yeah.
may need several thicknesses of it because the aluminum foil that you can get most easily is fairly thin. It's like you use in your kitchen, okay? And in that case, you need several thicknesses of it so that it does not tear when you put your test lead, clip your test lead to it. The important part is that aluminum is electrically conductive. And so we can easily apply that and conform that or put it in very close contact with the medical device, tape it down, and then just clip our red test lead to it. And we have created the same situation as would occur if the patient were to touch the medical device. And I'll go over this again. There's current flow and conductors inside the medical device. Those are conductors. There's the plastic covering on the medical device, the chassis, that is an insulator. And if the patient touches the medical device, the patient, as are each of us, electrically conductive. So we have a conductor, an insulator, and a conductor. That is a capacitor, and current will flow across from inside to outside in a capacitively coupled manner. We need to measure how much current flow is there, where is it flowing, and those are the questions that we have to answer. So that aluminum foil needs to be several thicknesses. There is nothing in the standard, I don't believe, that calls out a mill thickness of the foil, because that would make it very difficult to get a hold of. So just, my experience is if I take aluminum foil I can buy at the store and I use 2 or 3 sheets folded tightly together, that's usually, it won't tear very easily, and that's sufficient and allows the measurement to be made. There won't be very much leakage current there, but we still have to know how much is there and under what conditions is it flowing.
Okay. So next question is like, can you repeat if the ground is not clear? I don't know. Can you repeat the test if ground is not clear?
If ground is not clear.
Yeah.
You mean the voltage test? Do they mean the voltage test, or what are they talking about?
I mean,
My
it is
friends,
continuation. Yeah, continuation of the aluminum foil. Yeah, touch current. I think it's a little unclear.
yeah, I don't
Simple.
understand the question. My friends, you must ask your question with detail. Don't just
Yeah,
assume the other person knows what you're thinking. Okay,
that's true. Yeah.
please.
Okay. So next question is like, if one of the electrical tests like ground wire resistance does not comply with any standard, what do we do? Can
It's
you
failed.
suggest?
it has failed the test, you must find out why it failed, because it should not have failed.
Yeah.
If you have, I mean, there is a situation outside the United States and in different parts of the world where the manufacturers in that particular country do not pay very close attention at all to safety of the medical device that they're selling and giving the hospital to use on patients. That's possible. If you find that and you find repeatedly that it fails the tests from the international standard, do not use that medical device. It has to be corrected, or you get rid of it and you get a medical device in there that passes the required minimum performance and safety testing. It has to. Again, we're answering the question for ourselves, how do we want that medical device to work if we or someone we love is the next patient that will be connected to it? So if it fails a test, will you put that back into clinical use? And then your mother or your sister or yourself are the next patient that will be connected to it? Will you do that, really? No, you wouldn't. So if it fails a test, you have to find the reason for the failure, fix it, and repeat the test to prove that it passes. That is always the case. Always, always, always. We never say, oh, well, it only failed this test, we'll put it back into clinical use. No, 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 no. Our job is to make sure the medical devices in the hospital are safe and effective for clinical use. That's our job. Okay.
Yeah. So next question is, just a sec. So on the leakage current, how much is leakage current allowed to pass safety tests as manufacturing testing? I mean, that is a whole lot of. I
That
think you
is
have
an
discussed it.
IEC 60601-1 question, and it
Yeah.
is answered. It is answered in one or more of our other webinars specific about IEC 60601. And it is in the book chapter about IEC 62353. So where's the book chapter? You register for Advantage training. You take the course on electrical safety for medical device quality assurance. And in that book chapter, you'll be able to download that book chapter. And in that book chapter, it describes exactly what the testing limits are. Okay. We showed them yesterday for patient monitors. They're not going to be very different for ventilators, except that, as we said, we don't have any electrically conductive applied parts typically in a ventilator. So I encourage you to go register for Advantage training, go to that medical device quality assurance group for do the electrical safety one and download the book chapter.
Yeah, thank you. So next query is that what is the maximum chassis current from instrument to patient? I mean, again, it says the same answer.
The same answer. I'm sorry.
Yeah, correct.
Look, Jerry has a lot of answers for you, but I'm also, you need to use your own intellect, and I have already explained where to find these kinds of questions, the specific answer. Please go do the training. Make sure that you do all the training. If you just take a 1-hour webinar where you don't even put your hands on the test instrument or the medical device, have you really learned what you need to learn? Probably not. If you only took a 1-hour webinar, are you an expert? Probably not. So please go and avail yourself of the training. Take the training.
Yep. And the next question is this possible that compressor pressure in the ventilator affect the electrical damage? I mean, compressor pressure can cause an electrical damage. That's what is the query basically.
If the compressor motor short-circuited, but it's built into the ventilator. If a compressor is so if you have a ventilator and it has no compressor and you have no source for medical air, because that's all the compressor can give you, then you have a compressor that is a separate medical device called the compressor. That device itself needs its own electrical safety test first. Could it short circuit and cause an electrical problem in the ventilator? No, not in that case, because it's a separate medical device with a separate power cord connected to its own mains source. There's no electrical connection between the compressor and the ventilator in that case, where we have a standalone compressor. The compressor that is integrated or built into the ventilator is part of what you're testing for electrical safety already. And could a short circuit or something in that cause a problem? Sure, it could. Yeah, absolutely it could. And that's one of the things that we're going to test and make measurements and analyze our measurements to determine.
Okay, so next question is it mandatory to do electrical safety? I mean, BiPAP. The question is basically he is given a specific model Philips A40, but question is like any electrical safety test is required for BiPAP CPAPs.
Is it a requirement? If it is used
Yes.
inside a hospital, if it is sold as a medical device anywhere in the world, it has to pass the electrical safety requirements in the international standard. The country, each country may adopt or create their own local national standards, and how they enforce it within the country is different for each country. But I'm asking you the question about being a professional biomedical engineer. I really don't care whether your country has adopted electrical safety or not. If you're a professional biomedical engineer, you care about the minimum the safety and performance of medical devices, period. Either you do care or you don't care. This is not am I forced to, is somebody holding a gun to my head and saying, you will test for electrical safety? No, my friends, it's not about that. It's about being professional in what you do, what you've chosen to do for your career. Yes, it's required to do electrical safety to keep that medical device safe and effective for the next patient that will be connected to it. That's where it all begins and ends, okay? That is it.
Okay, and next question is, though it is not related to ventilator, but it says how to check P resistance for a class 1 device with no PE terminal. So example given is a
Well,
neon cotton
here's
defibrillator.
the short answer. If we are in the field, if we are in the hospital or in a clinic or wherever that is, we are not allowed to open the medical device in order to get at ground. We're not. We are not going to improvise a connection that would not normally exist. We're not going to do that. The standard nor anything requires us to do that. So if there is no protective earth test point, and that's a possibility, it would be in two situations. First situation, it's a class 1 medical device, but it's a hybrid. So there is no accessible ground or PE test point. Therefore, we cannot do that test. Guess what? We cannot do ground leakage to ground either. There is no test point for us to be able to make that measurement. So what can we do? We can and must do touch current leakage, because touch current leakage does not require the ground. The other situation that could occur is if it is a class 2 medical electrical safety device, which is double insulated, which means our power cord only has 2 prongs, no ground. It has a hot and a neutral. That's it. Okay, you will have no accessible ground on that device typically. Okay, third situation could be a class IP, internal power, which means battery operated. All right. So the question was, though, you have a class 1 device, but there's no accessible ground. Well, you mark on your sheet, cannot test. I wouldn't say not applicable. I would say not possible to test ground wire resistance, not possible to test leakage current to ground, not possible to test applied parts to ground leakage. But we can do all of the other leakages, touch current leakage and applied parts to each other. And we can do the mains on applied part tests. But we can't do what we can't connect to. You need to
Sure,
document it though, and you need to say what you're going to do in your medical device quality assurance program policy. It needs to say what I just said. When there is no accessible ground test point, we will not be able to test this, this, and this. We will test this, this, and this, other things. So you have to have policy and do what you said you're going to do.
Yeah. So next question, Jerry, is like, if the machine has ground and equipotential ground, which one should he place the ground probe? Means where should he
All
place
right,
the ground probe?
there's no. Okay, so equipotential ground is a power distribution system. It's the room that is equipotentially grounded. Okay, so we're talking about the medical device. The medical device has a protective earth test point. It's not an equipotential test point. I know people have called it that, but it's not the right name for that connector. All right. Now, would I use that connector to make sure that the protective earth of my device is connected to the equipotential ground point in the room? Sure, I would, but it's not called the equipotential test point. We're not testing equipotential grounding there. We're testing protective earth grounding of the medical device itself. Okay, I know that may be splitting hairs, we would say in English, you know, cutting it down to the really, really fine points. But the point here is, ask the question again, and let me see if I can address the real question. Ask the question again, please.
You want me to ask the question again?
Yes, this question, yeah.
Okay. If the machine has both ground and equipotential ground, where should he place the ground probe?
It should not have two different grounds. It should not have. It'll have one point, and that will be the protective earth ground point.
Okay, next question is how the equipment power and load current calculating is in electrical safety. Will it be accurate? How the equipment power and load current calculated in electrical safety? I mean, it's little vague.
All right, you're talking about the current that flows during operation of the device. Again, the question is asked in a very strange way. If we're talking about measuring the operating current, that's a different test. And yes, our safety analyzers can do that test. It is the ampere button, but that's not about electrical safety. It's about troubleshooting power-related problems in the medical device. It's not an electrical safety test at all. So it's outside the scope of this particular training. It is something that you should know, and you should know that what you can do with your safety analyzer. Look in the operator's manual of the electrical safety analyzer you're using and see if it has the ability to measure that operating current. We can do it. And by the way, the appropriate measurement when you're doing that test is with power on and the unit operating. You need to see the operating power. When you turn the unit off or even in standby, you're not going to see or be able to troubleshoot the problem. That operating current function of the electrical safety analyzer is there to troubleshoot with. It's not part of the electrical safety test. Doesn't have to be.
Okay, so one very basic question, like in what ways does the electrical safety analyzer differ from a multimeter?
It is a very
When we use it?
specialized multimeter with specific ranges that match up with the testing methods required in the international standards. A multimeter doesn't have the appropriate test load. You would have to improvise that load, and it's not standard. Therefore, it doesn't follow any of the standardization for metrology of the measurements. And your country, India, is a signer on the international agreement about metrology, so that all measurements that are made in India, if I repeat those same measurements in the United States, they will equal each other.
Yeah,
Okay, so
yeah. Okay, next question is applied parts, plastic parts are applicable for leakage current test. So you have already discussed, basically they have to go for touch current. Okay, next question is,
yeah, go ahead.
yeah, next question is how the equipment power and load current calculated in electrical safety. Will it be accurate?
No, we're not going into that. I just answered that question. Operating current, the power, it's not about that. That's not part of the electrical safety test. If you want to be an electrician or you want to be a power generator servicer, that's not what biomedical engineers do. That's not what biomedical engineers do. No, no, it's not part of electrical safety testing. Okay. It is a measurement that we would make if we need to troubleshoot. It's not a routine preventive maintenance test that needs to be done. We're not using motor generators here. Okay.
So, yeah. Okay, so next part of the same question, next there is the part B, how the equipment power and the load current calculated in using electrical safety tests.
It's the
So, I think,
same
yeah.
question. That
Yeah,
it's
okay.
not part of electrical safety testing. It's not part of it.
So, okay, we'll go to the next question. Electrical safety testing calibration. Can you explain difference between calibration done locally and firmware calibration at factory? Which one is appropriate and why? Firmware calibration. I mean,
The calibration
firmware.
of the test instrument, are we talking about, or the calibration of the medical device?
I think he's talking about calibration of the medical device.
All right. Well, when you make a measurement, you are calibrating by definition. If you think calibrating means making an adjustment because you found the device to be out of tolerance, let me answer the question in another different way. In the factory, all of the measurements that are made with testing standards. When we talk about standards in terms of metrology, the science of measurements, all right? We are totally traceable with those test instruments all the way back to SI units of measure, all right, in Europe. Traceable. Why? Because we make sure that when we calibrate anything, when we calibrate those standards, when we calibrate using those standards, whatever the measurement that we make is traceable all the way back to SI. Again, why? Because then a measurement that you make in India is the same measurement that I'm going to make here in the United States or in any part of Europe or in any part of South America or anywhere else in the world, okay? So the calibration should be done using a transfer standard that is traceable in an unbroken chain, including your test instrument that you're using, whether you're getting it from us or anybody else. So, which is better? The one that has a traceable measurement with an unbroken chain. That's the one that's better. So you have the ability to keep your test instruments calibrated in an unbroken chain all the way back to SI so that its measurement is appropriate. A calibration laboratory in India who is authorized to do calibrations should be doing the same thing that I've just advised you to do.
Okay, Jerry,
Okay.
we'll take another maybe two questions before we go to our demo. Last question, basically. So
Yeah.
there was one question like three-phase testing, basically, how to do electrical safety for MRI equipment or a three-phase equipment.
So that wasn't the topic of discussion
Yeah,
here. That
exactly,
was
exactly.
right. And I already explained that yesterday. You never will do testing on all three phases at the same time. Your testing would be done. Actually, that's a totally different situation anyway, because now we're talking about medical devices that are permanently connected to mains power. But even at that, in a MR room, it may be sourced from a three-phase power supply, but different parts of the room and different parts of that MR are powered from a different phase of that three-phase system. And to do any testing that's meaningful means that you need to be referenced to the appropriate phase. That's what you need to do. So it's a separate subject. There's a webinar available on our website about doing permanently connected to mains testing. I know it may seem confusing, and it is, but it's not part of this webinar.
Okay, I think last question will be, what is the burn test for to test ventilator after factory assembling or before dispatching? It's something different.
Burn-in tests are to find flaws and bugs in software. That's what they're for. We don't do those tests in the hospital, and even in the manufacturer. You don't do those tests on the factory floor. You do those tests in design while you're designing the device, and in design, you may not even do them in design validation. So that is a designer question. And again, outside the scope of this particular training, happy to have that conversation with you at some time, but it's not part of this kind of testing that we're doing. We're not going to do burn-in tests. You don't even find a burn-in test in 60601-1. Okay.
That's true. Yep.
The burn-in
So I
test
think,
is for a completely different purpose than any electrical safety testing.
okay, thank you, Jerry, for clarifying here. So I think we'll go for the hands-on demo. Over to Ravi. Ravi, you are ready?
Okay, let me stop sharing for a minute.
Yeah. Ravi. I think Maria Ravi is unmuted. Ravi, it's over to you.
Okay. Hope everybody is able to see my screen, I believe. Jerry, can you minimize your screen?
I have stopped sharing my
Yes.
screen, so.
Okay. Yeah, everybody is able to see my screen, I believe. Okay. Let us go. Actually, what we have right now today is a portable ventilator, which does not have a ground point, accessible ground point. So we are going to skip that and we do the touch current. And then before going to that, first part of the things yesterday we could not show. We are going to see the voltage available in the facility. Voltage available in the facility means if you are in the hospital, if you are going to check, you have to check the voltage between the line L1 and L2, live to neutral, live to ground, and then neutral to ground. Okay, first let me, I am showing the screen here. We are showing live to neutral. Next is actually we are going to do the thing live to ground. Okay. Then neutral to earth, neutral to ground. This is the first we are going to measure and note down the readings of the voltages. Next we go to the leakage, touch current. Touch current, as I have told yesterday, we are going to use a aluminum foil which is wrapped on the body of the equipment. You can see actually, can you show me that this aluminum foil? Aluminum foil, you just see we have wrapped an aluminum foil on the equipment and we are going to do the test on
So,
the touch current.
Ravi,
Yeah.
that aluminum foil should go on the surface of the medical device that the patient is most likely to touch. Therefore, not on the
Okay.
top typically, but probably on the front face. So can you
Okay, we
move
can
it,
do that.
please?
We can do
Yeah.
it. Yes. Just we do it that one also. Print
Thank
and
you.
then
Make sure it is touching that medical device completely.
yes, it
Okay.
is touching
So you
medical
may
device
need more.
completely.
Okay. You may need more tape in order to make sure it
Yes,
stays
yes.
where it
We
needs
are
to be.
going to put the tape so that it will be better. We have wrapped it and then we are going to test the touch current now. So to test the touch current, we are going to press microamps button which is available on the equipment. Okay. Please note that we are going to do AC plus DC right now and we are going to put our alligator clip to the aluminum foil. Okay. Now next test is we are going to do the single fault condition. Now it is in the normal condition. Single fault means which can be neutral open or ground open or phase reversal, line to neutral or neutral to line. Okay, we are going to do in one condition. We have changed phase reversal. We have done the phase reversing the polarity. This is a one single fault condition. Now actually I am going to standard polarity and then ground open. Please note that equipment has a built-in delay and it will not take immediately the change of single fault condition to other conditions. It will take 2 seconds time. Okay, now it is a ground open condition. Okay. Next current, now this is we are doing it in a direct method. Now we go to differential method. Same, we are going to repeat the test. Polarity reverse. And then we do ground open. Yes, it should be normal polarity when you are doing the ground open. Next is alternate. To make the alternate measurement, we have to press test. Please see there is a red light is glowing, which means you are not supposed to touch the equipment. These are all the tests we have to do. Yeah, then actually we have to do the same on the ground open condition. These are all the tests which we need to do it. Okay. Yeah, these are all the tests. Because we don't have a accessible ground, we are not going to do the ground wire resistance test. And then there will not be any applied parts. Please be remembered that ventilators will not be having any applied parts. We are not going to use that. And if it is, the applied part means if it is a any other than the triggering connections are there, electrical triggering is there, that can be an applied part. Otherwise, it will not be. Okay. Any questions you can ask. Now we go to insulation resistance.
So remember that insulation resistance is only required if the local national standard says it has to be done, or if the manufacturer of the medical device says that it has to be done. Otherwise, insulation tests are not required.
Yeah. To add to that, actually manufacturer will specify at what voltage, DC voltage. I mean to say, you need to do whether it is on 250 volts or 500 volts. Equipment will have the built-in capability of testing either 250 volt DC or 500 volt DC. See, you can change it to 250 volts or you can do it to 500 volts. I will do it on a 500 volts testing. Please be remember, whenever the red light glows, we are not supposed to test the thing. OL means ground by resistance is good. Okay.
Basically, it's greater than the testing, the minimum requirement. And so remember here, for the insulation resistance, we want a very high resistance to electrical current flow. So our source is, as Ravi said, 500 volts DC, and we're measuring, the measured value will be in mega ohms, 10 to the 6th power ohms, okay? And OL means over the limit, okay? It means it's higher than the minimum requirement. So it's a good measurement.
Okay. Next, actually, we don't do mains and applied parts or anything because ventilator doesn't have a applied parts. This is be noted. There will not be any mains and applied part test for a ventilator. Okay. Yeah. And then actually you can select the test, what standard you are going to do. You can do it IEC 62353 or IEC 60601, which is having a built-in tests. Actually, you will be able to see my screen is little smaller, I believe. You can select the test going to the setup menu. Any test you can do it, and then according to that you can do it.
And once again,
Okay.
you will verify the standard that is set into this electrical safety analyzer before you begin any of your testing. And you will make it match to what you said you were going to use as your standard. And in the case of IEC 62353, which testing method that you're going to be using. So you would set this to IEC 62353, and then while you're doing your electrical safety testing following the menus on our safety analyzer, you would use the direct method or the alternative or differential, whichever one of those that you selected, not all, just one. Okay. And
Yes.
that's how you make sure that your testing is compliant to the international standard in an appropriate way.
And another advantage about ESA 615 is you can set your flow in the sense You can prefix 62353 which equipment you are going to do, ventilator. These are all the programs it has to be run, and auto sequence can be run automatically. It will be guiding you how to do the test, and it gives the finally the results can be saved and transferred to your computer. This is an advantage. Whereas if you are using 612 or 620, if you are and then you can use an Ansur software or our 1QA software, which will be helpful for you to set a prefix program how to test a ventilator or a monitor, or of course any other equipment. You can prefix the program.